in this research, we have used mechanical ventilation. We decided to use mechanical ventilation with the proper use of building construction material and the use of ceiling fans to increase the indoor air velocity in times when the air temperatures gets high for thermal comfort reasons, can actually decrease the dependency on the mechanical vapor compression air conditioning system, and can also provide the thermal comfort and the indoor air quality. The study that we are considering would be simultaneously using local construction materials such as Srour as a replacement for insulation, the use of hemp in concrete, and the use of a mechanical controller to minimize the amount of outdoor air that we need to provide the maximum amount of comfort during the whole day or during the whole year inside the building. Now, in the literature, there are numerous studies that supports the use of mechanical ventilation. And actually, the efficiency of using mechanical ventilation to provide thermal comfort and air quality in the indoors, its efficiency really depends on the outdoor temperature, the building envelope material, and the control strategy that you will be using to admit the outside air. And also the literature have also indicated that the use of hemp in concrete is not only important for sustainability in buildings, but also the use of hemp will lower the conductivity of the concrete, and therefore the heat transmission across the building envelope will get lower. So this motivated us to use local materials like hemp, use Srour, and use mechanical ventilation to study this method as an energy alternative method for providing comfort in the buildings in Lebanon. To meet the objectives of this study, we have developed a mechanical ventilation controller that is integrated with a numerical multi-zoner space and comfort models. The model that we have developed, or the integrated model that we have developed, it requires the building material and the set of indoor conditions that we would like to have, and the set of outdoor conditions, and the model would output what is the needed amount of outdoor air to provide these conditions. We have developed a mathematical model for the space to determine the indoor temperature and the moisture inside the building, and for the heat transfer across the external walls of this building, we have used one-dimensional transient conduction, and we have, and also, as I said, we have developed for the temperature and for the humidity, because these are the two important factors that affect the indoor thermal comfort, the humidity and air temperature. And also we have developed a PID controller that will minimize the amount of air, because we need to cut on the fan power that will bring the outside air. So we have developed a PID controller for that purpose. And of course we need a thermal comfort model, and in this case we have used the Calcareos model, which is a scale from -3 to +3. Now, for the control strategy, we have divided the space into two zones, mainly one zone for the living room and dining room, and another zone for the bedroom zones. The occupancy schedule, for example, in the living zone, starts from 8 in the morning till 11 in the evening, whereas in the bedroom zone, it starts from 11 in the evening till about 10 in the morning. And we have allowed the controller to vary the amount of outdoor air to go from a minimum of 7.5 liters per second per person, as recommended by Ashley, for the minimum amount of fresh air for indoor air quality for people, and up to 25 air change hour as a maximum upper limit. Now, and for the control strategies, we decided to set the temperature during the winter time to 22 degrees Celsius, and the controller will be active during winter time in two conditions. Whenever the temperature inside the room is lower than the outside ambient temperature, and also the inside temperature is lower than the set point temperature which we have chosen to be at 22 degrees. Whereas in the summer conditions, the controller will be active whenever the temperature in the room will be greater than the ambient temperature, or whenever the temperature in the room is greater than the set point temperature. And in case during summer I'm unable to attain the thermal comfort, we have ceiling fans which will increase the indoor air velocity to minimize the discomfort. Now, for these objectives, we have developed an algorithm to simulate the model, and so we have the input conditions, the physical parameters of the building, the initial conditions. We simulate for the building to get the indoor temperature, the indoor humidity, and we compare the zone temperature, with the set point, and on the comparisons between the indoor temperature with the set point temperature and with the outdoor air temperature, the controller will decide on the amount of ventilation that we can admit to the building to reach the comfort level that we would like to have. Okay. After we have developed these models with the control strategies, we wanted to validate the results of the model. To validate the results of the model, we compared the results of the numerical model with the results of calibrated Francis commercial model, and the comparison for certain conditions during the year we have shown that the model results were correct. Having followed the validation, we moved into a case study. And for the case study, we have chosen a typical residential apartment in Lebanon of a floor area of 160 meters square. The living room area is about 100 meters square, whereas for the bedroom zone, the floor area is 16 meters square. And for the construction building material, the external walls were made of 15 centimeter concrete. This is what is typically being used in Lebanon. No insulation in the external envelope. Now, we decided to select different building materials. So for the base case, which is what is typically used, currently used, which is 15 centimeter of hollow concrete, this is the base case. And for we decided that we will be using different building material for the living zone and different building material for the bedroom zone. For the living zone, we decided to include insulation. And the insulation that we have decided to include, as I said, we will be using Srour. And for case 1, we kept the 15 centimeter thickness of the wall, which is currently being used in Lebanon. But this 15 centimeter is made of 2 layers of hemp concrete, each of 6 centimeter. And in between there is 3 centimeter of Srour insulation. For case 2, this is in the living zone, we used a more massive wall material, and the total thickness of the wall is about 25, because it is made of 2 layers of hemp concrete, each of 10 centimeter, and the Srour insulation that was used for case 2 is 5 centimeter. For the bedroom zone, we decided to use a lighter material, building material, than what is currently used. So we used 10 centimeter of hemp-free concrete. And another case, for case 4, we used, we kept the 15 centimeter but we included the insulation of 5 centimeters of Srour. Now, we run the simulation, and this for the base case, okay, and for case 1 and case 2, I'm talking now about the living zone. And during the months of February, and what we notice during the months of February, when the temperature is low, the controller was set at its minimum value, okay? Because the temperature outside is cold, okay? So the controller, okay, did not try, okay, to bring the outside air. It only brought the outside air that is enough for air quality. But what we have noticed for the living zone, that for case 1, because we have included insulation, the temperature in the indoor is greater than the temperature in the base case. The base case is the case where we are using the typical construction material in Lebanon, and we are using mechanical ventilation. So using the insulation, okay, in the living zone, okay, did increase the air temperature in the living zone. And the temperature in the living zone, it was a little bit higher even with case 2, where we have a massive wall. Now, for the bedroom, okay, what we have noticed that for case 3, which is the lighter wall, during the winter time, the temperature is lower, okay, and it is kind of higher for case 4, where we have used insulation. Now, we studied also during the summertime, and in the summertime, which is more, where the temperature can get higher in the indoors, we noticed that in the living zone, what the controller was trying to do, it was trying to prevent the temperature from getting riser than the outdoor temperature. Now, the controller was unable to bring the temperature to 26 degrees. But, okay, at the same time, the controller, okay, because it was unable to set the temperature to 26 degrees, okay, it did prevent it from getting higher than the 26 degrees, and we can see, okay, the periods where we had to use the fan. Finally, okay, we did, okay, the simulation for the different months, using the different materials. And what we concluded that, okay, with the mechanical ventilation is it is a viable option in Lebanon if we use massive wall material with insulation in the living zone, and we use lighter material in the bedroom zone.
Thanks so much. One question, if there's any. Please, go ahead.
Kamel, thank you for the presentation. I have a quick question. The U value for the different cases.
Now,
for the different cases, you give a different U value. How was it calculated based on the actual thermal properties of each constituent?
well, let me tell you, okay. For the hemp with coffee, we didn't measure it experimentally.
Okay.
In the lab.
Now, when I combine it with the straw, you come up with
it is combined, you know, with the straw. It is mixed with the straw, and we prepared samples, okay, and we measured the U value in the lab experimentally.
okay. And so when it's combined with the hollow blocks together, you come up with a new value.
The hollow block, we use what is reported in the literature, which is the base case. Okay.
Thanks so much. I guess we have to move on. Thanks so much. Next is a presentation on novel cyclometalated Ruthenium complexes and Electrolyte system for dye-sensitized solar cells, given by Dr. Tarek.
afternoon, everybody. In 5 to 10 minutes, I will just summarize a 2-year project that was funded by the Munib and Angela Master Institute for Energy and Natural Resources. We started by chemistry and we will end up by chemistry. Professor Fouché, I think, introduced the idea of solar cells, particularly organic solar cells, at the beginning of this session. I will end here with talking a little bit about inorganic solar cells using some organic materials. My talk will be about cyclometalated ruthenium complexes, one part, and a small part about electrolyte systems. Okay, this is I know it's a complicated graph, but it tells us a little bit about efficiencies of solar cells up to 2013. You see the organic cells and the organic tandem cells are somewhere here. What I'm talking about is today is Dye-Sensitized solar cells, which is also circular. You see the organic are starting to get better. However, for the last 10 years, we're stuck at the 10 to 11% efficiency. I came back from the Nano-GD conference yesterday, where Professor Michael Bacel, who invented the Dye-Sensitized solar cells, announced the 15% efficiency solar cell. So we are getting some. So just a little bit about the components of the Dye-Sensitized solar cell. If the Dye-Sensitized solar cell, we use usually a conducting glass, usually fluorine double tin oxide, with the titanium base made out of very small nanoparticles of titanium, which is a semiconductor. And then we attach the dye. The dye plays the role of absorbing the sound. So this is the first part of my talk. We'll be talking about these kinds of dyes. There's also an electrolyte system which regenerates the oxidized dye after rejection of electrons. And we have the counter electrode, which is also a conducting glass with a small layer of platinum as a catalyst to regenerate the electrons. The there are a couple of problems we still have to fix in order to commercialize DSCs. Volatility of the electrolyte system is a problem because usually these are liquid-based. Lately, people are trying ionic liquids, which do not really evaporate that easily. However, there's some mass transport problems. The use of corrosive iodine electrolyte is another problem because iodine will attack the contacts of the solar cell with time. Extending the absorption spectrum of the dye to the near IR is also very hard. And we also heard Professor Fouché talking about this. And also the long-term stability, because we need cells that live for more than 15 years in action. So, one of the best dyes that have been made until now is a dye called N719. It's very good. It's one of the best. It is the one that gave the 11% efficiency. The 15% is still a secret. We don't know what it is. However, the long-term stability is very bad. And I'll show you a couple of experiments that we did. One of the reasons behind this is the labile ligands on the ruthenium. So we wanted to design molecules that absorb the light in very good amount, but at the same time are stable. So we started making in our lab such complexes. These are called cyclometalated because we have a metal carbon bond here. These are robust because they are a chelating, a trichelate to the ruthenium, so it's very hard to break these bonds. In reality, in order to break, for example, the ruthenium carbon bond here, you need to boil this in concentrated sulfuric acid in order to break it. So these are very robust materials. So we made these 7 different cyclometalated dyes with different groups on the feather ring and on this building. And we made cells out of these. I will not talk about the whole thing. Just want to tell you about this red one. It's the T66, where we have a carboxylate here and nothing on the benzene ring. It had the highest extinction coefficient, absorptive extinction coefficient, that extended down to 750 nanometers. We use this in a solar cell. This is the answer material that I was talking about. These are the label ligands. We did a solar cell out of these 2. These are non-optimized solar cell, meaning we do not go to thick layers of titanium. These are just 8 micron. So that's why currents are around 14, but we can go up to 80 milliamp per centimeter. So as you see, the T66 gave similar currents to N719 and fill factor and same voltage. We did not beat it, but the long-term stability was much higher. These, the red one is for N719, the black one is for the T66. These are real solar cells that we shine light one sun for 1,000 hours, approximately 42 days, at 65 degrees. And we measure the efficiency every couple of days. As you can see, the efficiency went down from 5.5 for N719 down to 4. Whereas for T66, the first really a couple of days it increases, and that goes down by only 7%. So at the end, 93% of the initial efficiency was acquired. So this is for the first part. The second part, as I said at the beginning, one of the problems is the electrolyte system because it's iodine, it has a lot of problems. So we wanted to work with some organic electrolytes. So we tried this thion disulfide. So this is the reduced form, and this is the oxidized form. And we designed it in a way that it is soluble in organic solvents. At the same time, it has the right potential, oxidation reduction potential, and stability, of course. Then we make the cells. Usually we use platinum as the counteractor, a thin film of platinum as counteractor. Device A is just N719 with this new electrolyte system with platinum. Gave us very low values of current. Voltage does not change because we are not changing much the redox potential of the electrolyte and the titanium. However, platinum was a very bad counter-electrode. Even the fill factors are low on the low side. That's the problem for in the SEC field. When you change one parameter, the whole thing changes. So you have to work now not only with the electrolyte but also with the counter-electrode. So we wanted to find new material for counter-electrode. One of the materials that people use is cobalt sulfide, a thin film of cobalt sulfide. We tried this and the efficiency went much higher. It's this black one, up to 4%. But still, we should do better. I will not go over impedance spectroscopy. During this time, I met a person, Mustafa Musameh, who works, he's a professor that works at Srour in Australia, where they make what they call multi-wall carbon nanotube webs. These are the webs. They roll them. They make a forest of carbon nanotubes. These are, I will show you some pictures of these. And then they just draw them from the forest, and they make, it's like silk, just like silky material. And we can put them on electrodes. Okay. So these are the one layer. So if they draw one layer of these multi-wall carbon nanotubes, they are around 50 nanometers thick, and they will absorb only 20% of the light. In reality, we don't care because in this case, the counter electrode for the light is coming from the titanium. So for our purposes, we don't care about the transparency of the counter electrode. As you increase the number of layers of these carbon nanotubes, the resistance goes really down to 400 ohms per centimeter square. Some pictures of these. So this is a 50 CNT web layers. So these are 50 layers of CNTs that we can manipulate in the lab very easily. This is an SEM picture of before and after the densification. The way we stick them to the FTO, we put them on the FTO and you drop a drop of acetonitrile or acetone and leave it till it evaporates, it densifies and it gets stuck on the FTO. This is another SEM image. This is the DEM image of the multi-wall carbon nanotube. So this whole thing is the multi-carbon nanotube, and you can see it's around 8 carbon nanotubes within each other. And this is a photo of the electrode that we made in our lab. And when we did the cells with these, with 5 layers, we did not have to go to 50 and 100 layers. With 5 layers, we got a 3.86. 10 layers, 4.11. And after that, 20 layers, 4.12. You see, the fill factors got much better. Currents are approximately the same for the 5, 10, and 20, but they are much higher than the black machine. We are still working on the long-term stability of these of this new electrolyte. I just want to mention a little thing here, that as we increase the number of layers, the series resistance in the solar cell diminishes. So as we go to the 20 layers here, the series resistance went down from 12 down to 8 ohms per centimeter. So in conclusion, we successfully synthesized 6 different cyclometalated ruthenium dyes, and the long-term stability was really good for these dyes. And I think nowadays most of the dyes that people are making are using this kind of strategy, the cyclometallation. Also, we made a new organic-based electrolyte system. By the way, this new electrolyte system applies to solar cells and batteries at the same time, so it's really the same idea of the opposite reaction. And multi-wall carbon nanotubes was, for the first time, used in Dye-Sensitized solar cells. Thank you very much.
We can entertain a question or two.
Yes, sir.
So, why do you think it's nickel sulfide really better as catalyst?
It is. Cobalt sulfide is catalytic. The question is why? Nobody knows. Okay. Lately, we're working on a new electrolyte system, and we're doing a combinatorial kind of searching for a counter electrode, because there's no way to know which counter electrode will work with which.
So this is specific to the electrolyte. This is specific to the electrolyte.
Is it specific? No, it's not. It can be used with, it works with iodine, but not as good as platinum. I think platinum doesn't work in our case because it's thiols and they can absorb to the surface and inhibit reactions or stuff like this.
Sure. The use of ruthenium in particular, is it for the time span of the solar cells, or more for the efficiency?
It's really because
Okay. The good thing about ruthenium, it's robust. It absorbs light if you design the ligands the right way, but at the same time, it has something called a long-lived MLCT, a metal to ligand charge transfer. And this is something very important to inject the electron from the excited dye to the titanium and get a charge separated state. People have used iridium, but the problem with iridium is very expensive and doesn't absorb that much in the visible. They use ozonium. Ozonium is very good, but it is much, much more expensive than gold and platinum. So that's the problem.
Thanks so much.
Thank you.
Source rocks within which hydrocarbons are generated is a very important aspect of petroleum research. Dr. Ali Haidar actually will be presenting a paper on that line on Calcareos Nano-Fossil Biostratigraphy of the Paleocene-Eocene succession of the Chekka Marl formation in Lebanon, which actually we think that it is the source rock for the petroleum and gas here in Lebanon. So the
We're going to talk about the Calcareos Nano-Fossil Biostratigraphy of the Paleocene-Eocene succession in Lebanon. Basically, we are looking for petroleum prospects and to know if any set of rocks, any Lebanese formation is or has the potential of producing petroleum. We need more than one type of analysis. One of them is to determine the age, and the other is to know its geochemistry, to know if it can produce rocks, petroleum. Sorry. We went through this area here in Chekka and collected samples. There is a nice outcrop over there, and we got 220 samples from this location in North Carolina. And so the samples we're collecting from the Chekka Marls, which means the material is kind of soft rocks, and we collected 220 limestone and marl samples. It's a succession of 127 meters of thickness, and we collected samples each 20 centimeters. Now, in some intervals, it was not possible to do that because there was cover, vegetation cover. But in all the other places where the layers were cropping out, we collected samples, one sample every 20 centimeters. This is an example of a variety of these samples that gives you an idea about how soft they are in some cases, how hard they are in other cases. The color might be an indicator of their content of the organic matter. And these samples were subject to different types of analysis. First type of analysis is biostratigraphy, which means to determine the age. This is a geologic map of Lebanon. Geologic map means a colored map, and each color determines the age of the rocks that are at the surface, which means some preliminary work has already been done. This is the area of Chekka here, and so basically we are interested in this color, and if we look at this color, it's late Cretaceous Neogene, which means second geologic era plus third geologic era. But when we went to the samples and we made analysis, now we will see that the age here indicated on the map is not really correct, and we have a more correct map and more correct age and more detailed age. The interest of working on the onshore part, which means on land, and determining the petroleum prospect is that these Lebanese formations, the different colors indicating different types of rocks at the surface, are plunging down below seawater and making a thick stratigraphic succession. This is a seismic profile. This is not my work. This is from other companies' work. And it shows how the rocks extend for very long distances. Each of these has a different geologic age. Basically, the Chekka Marl is somewhere around here, So we can take samples from land, but this gives us the petroleum potential, and that would give us an idea that these rocks buried at few kilometers depth, how much petroleum they could produce in the sea after they drill here, which means we are trying to know how much petroleum there could be produced even before drilling. And the method is for the biostratigraphic part, for determining the age, we use light microscope, and at the end we label the species based on how abundant they are. Some species we find a lot of them. We are talking about Calcareos, Nano-Fossil species. These are microscopic fossils. We are talking about size from 1 to 10 microns each. And after determining the abundance of them, of each type in each sample, we construct the age. This is a summary of the results, of course. And here is a selection of the samples, sample 1, 21, 41, etc., which means every 20 samples here we are showing the result. And this is giving us the exact or detailed age. We are going from mid-Paleocene to early Eocene. And definitely the boundary at the top is more detailed, Tametian Ypres. How do we determine the age? Because we have different fossil species. Each of these, not each of these, some of these, at least those labeled with color, have been considered as a marker. They determine the age. It's known what is their specific age. And from their name, we can decide about the age. And these are the Calcareous Nano-Fossil zones for the Paleocene and the Paleogene. And so we can link the different species with their different age. As a result of this first part, which is biostratigraphy, determining the age, we have found Fasciculitus tympaniformis, Electrolyte clientele, Discoaster mulleri, Discoaster multiradiatus, and Romboaster drumleti. And these are the key species that indicate the age. And based on that, we decided that it is Paleocene-Eocene. After having done the age, we went into geochemistry. This is the lithology of the area, mainly limestone with marl. And we have done a set of analyses related to the hydrogen index, the organic carbon, the source potential, the maturation, etc. So we have all kinds of geochemical indicators. Plenty of examples on this. I'm showing only a few of them, and the result is here. We are having the total organic carbon. When the total organic carbon reaches a certain value, which means after this line here, we consider the amount as good, and the amount here is maybe poor or nearly fair. So there are places, there are at least 3 intervals. This is 1, this is the 2nd, and this is the 3rd. There are at least 3 intervals in the Chekka marl formation where we have good potential, because on the graph we can see that the values go up to this category in terms of total organic carbon. Of course, this is alone not enough, so we would like to know the degree of maturation. It's not enough to know how much organic carbon, also we have to know the maturity of the source rock. And so we use an S2 index for that, and even in these 3 intervals we have some good values. And we do use the hydrogen index, and even here. The hydrogen index is basically used to tell us whether we are more on the source oil as being oil, source rock as being oil or gas. And we can see if we go to this yellow color here, we are more in the gas-prone area. If we are more on this green part here, we are more on the oil-prone area. And if we are in the middle, it's a mixture between oil and gas. And of course, we cannot look at all the parts. We are only interested in those parts where we have good amount of organic carbon, which means only at these 3 intervals here. And we can see that these intervals mainly are in the mixed part, plus some of them are in the oil window more than the gas window. This is very good in respect in terms of economic prospect, because we know to generate the same amount of energy. If the product is gas, it costs less money, and if the product is oil, it's more expensive on the market. So that's good news between brackets. And so the results of the geochemistry, We have source rocks that are appearing locally, which means only at determined interval, not the whole section is productive. The whole section is 127 meters. I compressed it into 47 meters, which are those where I was able to collect samples. And within these 47 meters, there are 3 intervals that are productive. And so there are 3 main intervals. The first is between this and that sample. The second is between this and that sample, etc. So the Chekka source rocks are characterized generally by high total organic carbon content and fair potential to generate oil and gas. Also, the Tmax value, the pyrolysis Tmax value, indicates a range in terms of maturity of this hydrocarbon between thermally immature to marginally mature. So they are not extremely mature, but still they are capable of generating good hydrocarbon. As conclusion for my work, so mainly oil and gas prone source rocks could be distinguished throughout the analyzed 127 meter outcrop section of the Paleocene-Eocene Chekka Marls. The age is Paleocene-Eocene. The source rock appeared locally, which means only through some intervals. And we have 3 main intervals that can be productive, and the formation shows great hydrocarbon potential in terms of oil prone and gas prone. Thank you.
Great timing. Any questions on this? Actually, I have a question from the seismic profiles, offshore seismic profiles you have. Were you able to find out the thickness of the Chekka formation? The offshore and the onshore, of course, we know it, we can measure it, but from the seismic profiles, I don't know if you were able to look into this. Yeah.
Here we have the time basically that is nearly converted into meters. So from here to there we can talk about, I'm not sure the values are easy to read here. But the original is not time, it's not depth, it's time of migration of seismic waves up and down. So here it might be about 200 meters, the thickness of the Chekka formation. It extends basically over about half, at least half of the whole exclusive economic zone of Lebanon. So we're talking about huge areas, an amount of square kilometers equivalent to more than the surface of Lebanon. That means that even if we're talking about few percent total organic carbon, we are talking about a huge distribution over a few hundreds of meters. And the hope with the Masri award is to extend this work over all the formations of Lebanon so that we can model not only this part here, but all of these in future research work.
Can you give an estimate of how much oil and gas are there in Chekka based on analysis? Can you give an estimate of probability distribution of how much oil and gas we have, for example?
There are estimates. This is actually a small part of a larger work, including sections from outside Lebanon. And I'm working in collaboration with a company, Stratochem company in Egypt, and they have done a model on that, and there are technical estimates of the resource and real estimates. Before we drill, before we get anything, we do the model, that's the technical estimate, but we cannot sign a contract based on that. Once we drill and we have everything, that is the real estimate. The technical estimate might place Lebanon, I'm not talking all about Chekka formation in general, as one of the best 5 major producing countries in the world of gas, which means something like 8 below Qatar or so. This is a huge.
Thanks so much.
The design and development of an efficient and environmentally friendly charcoal production process. This work has been done as part of the master thesis for the Rashad, our student, and in collaboration with my colleagues, Asmar and Shammas. So in fact, charcoal is one of the oldest and the most common alternative energy method which has been practiced for thousands of years. The main reason for using charcoal is its high calorific value and the low emission when you run or when you operate with charcoal combustion methods. However, the limitation with charcoal is the fact that it contributes a lot in deforestation and causes a lot of environmental damage. So if we can improve the charcoal production process, therefore we can help minimize environmental damage as well as make it more attractive. So the objective of this research was basically to design a unit or a process whereby we can generate charcoal more efficiently by doing some heat integration, minimizing some of the emissions, and therefore increase the yield from the unit. We have to follow a systematic approach whereby we do a theoretical study on the unit by doing some CFD simulations, and then we design the unit, operate it, test it, and take the experimental results to validate our analysis. So as a background, the charcoal production process takes the route of the pyrolysis, whereby wood is subjected to high temperatures around 550 degrees in the absence of oxygen, and the main product is charcoal. However, this process will release a lot of vapors and gases which can be easily used as an energy source, either for power generation or for producing petrochemicals. Even they can be fed back into the system to sustain the combustion and help throughout the whole process to make it energy neutral eventually. The charcoal carbonization will basically evolve over a number of stages. So initially, around 110 degrees C, the water is driven off from the wood. Then temperature will rise up to 270 degrees, where the light hydrocarbons will be emitted or released, such as methane and CO2. Then as the temperature reaches 270 degrees plus, it becomes exothermic, so a lot of energy is released from the system, and the temperature will continue to increase. Eventually, all the tiles are driven off, and you end up with a high carbon content product. And this carbon content product is basically has got a very high calorific value, and it's a good source for energy. So historically, the way they produce charcoal is that they dig a pit in the ground, they put the wood, and they cover it. So initially, around 110 degrees C, the water is driven off from the wood. Then temperature will rise up to 270 degrees, where the light hydrocarbons will be emitted or released, such as methane and CO2. Then as the temperature reaches 270 degrees plus, it becomes exothermic, so a lot of energy is released from the system, and the temperature will continue to increase. Eventually, all the tiles are driven off, and you end up with a high carbon content product. And this carbon content product is basically has got a very high calorific value, and it's a good source for energy. So historically, the way they produce charcoal is that they dig a pit in the ground, they put the wood, and they cover it with earth, and they leave it over 1 week to carbonize the wood inside. At the same time, it's releasing a lot of methane gas and other, hydrocarbons into the atmosphere. And the fact that methane is more dangerous into the greenhouse effect, like 20 times more than CO2, so therefore you need a way to avoid releasing those gases into the atmosphere, or use them as an energy source instead of damaging the environment. Typical process time, like I said, is around 1 week. The yield is around 15 to 17%. It's labor intensive. Sometimes the kiln will catch fire and they have to repeat the process all over again. And like I said, there's a lot of emissions released into the atmosphere, so it's damaging to the environment. So we need to improve from this. So we went also through the literature research, and since the 90s, a lot of teams have researched about biomass and energy alternative from wood, and they basically developed a retort for different furnaces by combining drying and carbonization at the same time, and it's still underway. So our team basically went through the actual theoretical analysis and modeling of the unit. So we come up with a design, we analyze the performance of the design. If you're happy with it, then we continue with the actual construction and building of the unit. Otherwise, we can modify it, re-simulate again, and improve from it. So the design that we came up with is basically a double concentric pipe approach, whereby the inner pipe will contain the carbonizer, the outer vessel will contain the combustion zone. So the wood that I want to carbonize is basically sitting in the inside furnace, and the outside will provide basically the energy to ignite or to reach high temperatures. Also at the same time, the combustion zone, the exhaust from it will be fed back into the carbonization units to help dry and increase the wood temperature to reach carbonization temperatures. So in essence, we use the shear stress transport model, the K omega model, to help solve for the different turbulence and laminar regimes, for different pressures and flows, and at the boundary layers around the ball and in the wood side as well. We had also to specify the boundary conditions for the inlets, the outlets, as well as specify the heat sources, and we assume that the carbonizer can be more as a porous medium. So it's a porous space whereby the air will flow around the wood and will exchange heat by convection. These are some of the simulation results obtained from CFD. It shows the temperature profile across the unit and through the recycle line. And the temperature ranges around 500 degrees at the bottom of the furnace, all the way up to the exhaust, which is around ambient temperature, which is around 30-35 degrees. This is a closer look at the temperature profile in the vessel. This is another profile for the velocity, just to make sure that there's no backflow or any choking in the unit, just to make sure that the combustion takes place properly. So once we happy and identify that this design is feasible, we proceed with the actual construction and machining of the unit. So it shows exactly the actual inner turbonizer, which is surrounded by the combustion zone and all the recycle streams. Here's the instrumentation and piping units and the valves and different recycle streams. And this is the final unit with the actual temperature sensors, valves, induction fan, and an exhaust fan to help create a pressure differential between the inlet and the outlet. Now quickly I'm going to show you a demonstration of the actual process running. So this is where the process just started. As you can see, there is some fumes just leaving from the exhaust. The temperatures are still moderate. So we're talking around 500 degrees in the combustion zone. This is the exhaust temperature, which is 26 degrees. This is the induction fan. That's the recycle stream, 331 degrees. And this is the carbonizer temperature inside, where the charcoal is being made, around 400 degrees. So after 10-15 minutes, you can see a lot of methane is being released into the atmosphere. This is when the carbonization is taking place. It's only from 5 kilograms of wood, you can see how much we are releasing methane, which is a variable energy source. Now we are flaring, so now I burned it instead of just emitting it into the atmosphere. So I could easily use this methane as an energy source to drive a turbine, or just to convert it via reforming into methanol or other chemical compounds. So just again, as during the full carbonization, you'll see that the temperature is quite high. So it's around 270 in the recycle stream. But mainly you can see that the carbonizer is now operating at 900 degrees C, which is really high temperature compared to what the traditional methods do. They only achieve 550 degrees, whereas in our unit we reach 900 degrees of temperature. So this is another shot which shows the actual charcoal is sitting inside the carbonizer. So we took this charcoal and then we analyzed it to determine the moisture content, the ash content, as well as the carbon content. And each one of them, they need a specific method to analyze and determine in order to identify how much yield or how much carbon we obtain. So if we run the experiment at 550 degrees, we achieve 46% yield, so there's an improvement from 15%, which is a marginal improvement. The carbon content in the charcoal was around 73%. At the same time, we managed to run the whole experiment in 1 hour and about 15 minutes. And we achieved this result. Another example, for instance, is when we reached 900 degrees C, the carbon content was around 87%, pure carbon in the charcoal. And the yield obviously went down to 37% because at higher temperature we are driving more volatiles and more hydrocarbons from the top. But again, the timing was much shorter, 2-3 hours, high yield of at least 35 to 40%, and the quality of the carbon is quite high in comparison to traditional methods. So by improving the yield from 15%, we would have saved so much on deforestation level. Now the next stage is basically to improve from there and use the methane as a source for power generation, or we can do some reforming of the methane to produce other petrochemicals such as methanol or usable chemicals. So this will be the next stage of the research, hopefully next year. And I would like to thank the Munib Mastery Institute for supporting and funding this program.
The last presentation is co-authored by Professors Ali Yassine, Bacel Maddah, Mahmoud Fadi Nader, with first-year graduate student Zeaiter, and it is the title is Multi-Objective Optimization for Contract Areas Delineation and Sequential Basing of Lebanon Offshore and Starboard Assets.
It was so in the class, I was
By the time you get the last presentation, it's actually like something to start with So this research is aimed at This research is aimed at finding a new approach to finding carbon policy from the consideration phase of exploitation. It was conducted by myself and Professors Mahmoud, Elie, and Maddah. I would like to take this opportunity to thank the Nano-Fossil for their generous contribution. Now, we started by asking and wondering what a discovery offshore Lebanon would mean for the country, especially to answer the question of whether there is anything we can do today to improve our standing, or whether it is still too early to analyze. Now, why I ask if it's too early is because projects like this have a lot of complications. Most troubling are the uncertainties of price and the reserve volume, which cannot be known before production takes. The fact that two parties have to agree, the national oil company and the state, before any production takes place, the contract that compensates both also complicates matters, and the fact that infrastructure needs to be found to use any production that is made further complicates these things. Now, the model we present uses inputs instead of these uncertain values, uncertain inputs, and then generates a scenario. It solves the scenario to return the optimal PSC parameters and allocations that generate the maximum value for the state. And then we will vary these inputs to study the variability across the strategy across this expected range. So now we're going to go through a quick run of the model. It begins by taking volume inputs and determining the production profile seen here in red. This is a typical production profile for a gas field. It has a quick ramp up, a sustained plateau, and then finally decline to set in. So if we know the volume and some field characteristics, we can anticipate what the production profile will be. Now from this point, if we have the price of natural gas, we can understand which contracts will be attractive to investors and which will not. The model generates all these possible contracts, rules out the ones that are not attractive to investors, and from the remaining ones, it proceeds to optimally allocate the government's share of natural gas. We assume that each use produces a certain value for each unit of natural gas allocated to it, and we seek to maximize the value generated to the state across all these uses throughout the entire production. Now, the model presented here for and applied to Lebanon has only two identified uses, which are power generation and exporting. So the model takes inputs of costs, volume, and prices, and it tries to determine the PSC parameters and the allocations of natural gas from the state's side. This is the formulation. You can see up top, this is the maximization, where we model both uses. The rest define the parameters used in this model, and they define some constraints and the attractiveness of the model to investors. And now we will discuss the inputs for the case of Lebanon, the ones that were determined for this model. Now, in Lebanon, the expected range of reserves is anywhere up to 2.1 trillion cubic meters. We investigate this range in increments of 140 billion cubic meters. On the farmost left, you can see the size, the expected size. On the far right, we have the total cost. You can see that even the smallest fields require an operating investment of $1.7 billion, so it's a very expensive operation offshore drilling. And the larger fields, they go up to $26 billion. Now, these costs were found by benchmarking East Mediterranean projects and quoting well costs and production rates. Here we show the power demand expected in this model. We also show the demand rate and the peak rate. It is an assumption of this model that by the time production takes place, Lebanon will have the infrastructure to meet the demand of the area. Now for exporting, Lebanon has an infrastructure decision to make. It is already linked to the Arab pipeline that can export to any of these 4 countries up to 10.3 billion cubic meters per year. However, it can also commission an LNG plant at an assumed cost of $6 billion in order to export globally, and it will not be constrained by the pipeline. So this is an infrastructure cost that must be made. Finally, the contract there are 4 contract parameters regarding the PSC parameter. For the case of Lebanon, according to Lebanese law, the tax is fixed at 23.5% to be taken in cash and not in kind, and so it was excluded from our analysis. Furthermore, we found that contracts with royalty always have a 0 royalty equivalent, making royalty redundant. So this was also excluded from our analysis, leaving only cost recovery and profit sharing. Now we will cover the results for Lebanon and show just a couple of instances of the inputs which we changed to the analysis. So this is the solution across the field, across the expected volumes in Lebanon. You can see on the x-axis the volume increases. The shaded area is the value to the state. It's no surprise it increases as volume increases. The 2 lines here present the contract parameters, the optimal contract parameters, the ones that produces the most value to the state from this model. We noticed that there are 3 ranges, which we term small fields, medium fields, and large fields, in which the fields act very similarly to one another. So the first range is up to 700 billion cubic meters, in which the cost recovery, which is the dashed line, is at 100%. The second range is from 700 to 1.26 trillion cubic meters, where the cost recovery and profit share both fall slightly. And the final range is from 1.26 upwards, which is when they both increase. Now, fields in each range behave similarly, and so we will show one allocation solution for each of these fields. Now, for small fields, okay, in this graph, the larger light shaded area is the operator's share of the reserves. The smaller, darker one is the state's share of reserves. The solid black line is the power demand expected, and the blue columns here indicate that the entire government's share of reserves are allocated to power generation. You can see because cost recovery is at 100%, the state does not see inflows of gas until its 7th year, and that's when the operator is paid back for his investment. And after this point, everything is allocated to power generation without ever needing power generation. These fields are very small, they're very expensive, and they will only generate a value of around 4.5. This one will generate a value of around $4.5 billion in this state, which is really not that very much. Now, for medium fields, everything improves greatly. Since cost recovery has dropped from 100%, we do have early inflows of gas to the state. The state can meet its power generation up to 20 years, and for a period of 5 to 10 years during the middle, there is enough excess to export. This excess is slightly under 5 billion cubic meters, and so it can be handled by the pipeline. Fields in the medium field generate around $30 to $40 billion, which is substantially better than small fields. As for large fields, it improves even more. The state can meet power generation comfortably for the first 25 years, and there is a 15-year period of excess, where the excess is still around 10 billion cubic meters, which means it can be handled by the pipeline. There is no need to commission the LNG plant. This field, this large field, has been evaluated at $54 billion to the city. Now, since all these exports can be taken by the pipeline, you can see here that the results show value generated by the pipeline in the dashed line is always greater than an LNG plant. These volumes do not justify building an LNG plant. However, we found that for varying the gas price, if the gas price was higher, LNG plant becomes a justified option. This is because higher prices mean that the operator requires a smaller share of the reserves to meet his costs and his investment, and this would leave more in the hands of the government, meaning that you will have more to export making LNG. And as the price rises, the threshold for how large a field must be to justify this investment goes down. Here you can see graphically the improvement in value to the state as the price rises. Finally, we've been assuming that a 12.5% rate of return to the investor will make this project attractive to the world. However, we wanted to see what would happen if the investor would accept 10% or 15%. You can see for 10%, there is an increase in value for the field, but only a slight decrease across the entire range. Whereas for 15%, it is a large, substantial decrease in value for the state, making even small fields infeasible, meaning that if the operator were to come in and exploit the entire field and take it all to themselves, they will not make 15%. This is how small and expensive these fields are. Finally, as for conclusions, I'd like to stress that our contribution here is not these results, it is the idea that tying in the modes of monetization of the natural gas will have an impact in the pre-exploration period of generating the hydrocarbon policy. For Lebanon, we should expect very low royalties, very high cost recoveries to pay back the investor as soon as possible. These are results we run into in the literature as well. This is usually how it goes. Paying back the investor early on means the state gets to hold on to most of its reserves. Finally, there's ongoing research we have by my friend and colleague Elie and my research team to account for the price and volume variability not accounted for this one. Thank you, and I'm done.
Thank you very much for this. All that I want to say at the end, thank you all for attending. The names of the steering committee were not mentioned in the beginning, so I have to say their names. Those are Professor Abdel Fattah Abdel-Rahman, who's sitting here, Professor Fadi Al-Alid, Professor Farid Shaban, Professor Mahmoud Al-Hindi, Professor Ali Yassine, and Professor Bacel, who was the star of our steering committee this year because he took the heat for getting the invited speakers agreed to come. Thank you all for the participation and thank you for the family Masri for their presence and showing support, not only by funding the projects but also being here present today. Thank you.